Hello, I'm Kathryn Hamilton, and today I'm going to present benchmark calculations for electron collisions with neutral indium atoms. This work was carried out with my colleagues Oleg Zatsarini and Klaus Bartschat at Drake University, and also Dmitry Fursa and Igor Bray at the Curtin Institute in Australia. We are thankful for funding from the National Science Foundation and the Australian Research Council. Atomic indium has many applications. These include making transparent electrodes in LCD displays, and it is also a possible candidate to replace mercury in low-pressure discharge lamps. It is also suitable as a tracer for two-line atomic fluorescence thermometry, and its spectral lines are expected to be important in modelling plasmas in which indium is a constituent. Despite all these applications, there currently is a lack of electron-indium scattering data, both theoretical and experimental, available in the literature. The overarching goal of this project, therefore, is to provide a set of accurate cross-section data over a wide energy range, which can be used in gas discharge and low-temperature plasma modelling. And for this work today, we are going to focus on the electron impact excitation of the 5s squared 5p to the 5s squared 6s transition in indium. To study this, we are going to use two different numerical methods, B-spline R matrix and convergent close coupling. Both of these methods seek to solve the close coupling equations, BSR using an R matrix approach. The BSR method has two defining characteristics. Firstly, it uses a B-spline basis for its radial functions, and it also can use non-orthogonal bound and continuum orbitals. This ensures a high level of accuracy with compact configuration expansions. CCC uses an integral equation formulation for solving the close coupling equations in momentum space. It has a complete square integral basis, and convergence can be obtained by simply increasing the basis size. It can currently handle quasi-1 and 2 electron systems, so for this particular application to indium, CCC cannot open the 5s shell, whereas BSR can. Figure 1 shows the angle differential cross-section for electron impact excitation for 6 different incident projectile energies. The most striking feature on these graphs is the pair comparison between the relativistic distorted wave calculations and RCCC and DBSR and the experiment. However, even though comparison at high incident projectile energies and high angles is poor, the RDW calculations do agree quite well with the rest of the results presented at low scattering angles. And as they are weighted the most heavily when we calculate our integral cross-sections, the integral cross-sections from RDW calculations may not be completely inaccurate. Here in our legend, where RCCC and BSR are labelled with a particular number, that number indicates the number of states in the configuration expansion. Overall, for all the different incident projectile energies, DBSR and RCCC agree very well with each other and agree satisfactorily with the experimental results. From these angle differential cross-sections, we can go on and calculate angle integrated cross-sections. Figure A shows the comparison between our different levels of our DBSR and BSR models. With the bright red DBSR 214 state calculation represents our best model in this body of work. Here, the DBSR models include relativistic effects in our atomic structure, whereas BSR ones neglect them. However, we cannot distinguish if these relativistic effects come from the atomic structure or from the collision itself. Figure B shows a comparison between our best DBSR model and the relativistic convergent close coupling model containing 75 states. You can see here that the agreement between these two calculations is excellent. The agreement with experiment is also very good as well. Finally, here in table 1, we show oscillator strengths for 2 transitions in indium as calculated from our DBSR model. and you can see the length and velocity results compare very favourably to the NIST values. We also calculated our ground state polarizability as 64.5 A0 cubed, which falls well within the experimental values of 56.1 plus or minus 18.2 A0 cubed. To conclude, we generally see excellent agreement between our BSR and our RCCC calculations. Particularly for the integral cross-section, we believe a recommended dataset could be formed by taking an average at any energy between our RCCC results and DBSR ones, and this would yield an uncertainty of roughly 10%. In our angle integrated cross-section, we can see near the threshold structures which could possibly be Feshbach resonances or Wigner cusps. However, more detailed calculations are required before we can classify these. If you're interested in the results shown on this poster and the BSR and CCC methods, you can try these for yourselves on the AMP gateway at the link shown below. Example inputs are provided on the website, and you can run the codes interactively through your web browser. Thank you for your attention, and if you have any questions, you can contact me on Twitter as Atomic Kathryn, or use my email address kathryn.hamilton@drek.edu. Thank you.